All right, so this is a continuation of lecture 17. So the previous lecture video that you saw had to do with finishing up the weak acid with a strong base. So now I just want to talk about some finer points of titrations. One is polyprotic acids. So if I have a diprotic acid, like, H2A as a generic form. What I've been teaching you all along is that is a step-by-step process of where you are losing the H. So each step is an equilibrium. And each hydrogen comes off one at a time. So if we were able to do this titration, and actually the titration does not work that well, actually, you would be able to figure out how much of, or you would see a titration curve like this, where you would have what we call two equivalence points. So the first equivalence point is for the first hydrogen to come off, and the second equivalence point is for the second hydrogen to come off. So what they're trying to show you in this picture is the fact that it has 8 milliliters to get to neutral and then 16. So it is going to be a point by point, meaning that volume is going to be determined by the concentration, but it's going to be essentially equivalent. The other points that they're trying to show you here is midpoint 1 is essentially your pKa. So again, going back to that first hydrogen that comes off, this is a Ka1 and this is a Ka2. So that first hydrogen comes off, that's going to be, again, if you take the negative log of it, it's going to be where that number lines up. And then if you go across here, this is going to be your pK2. Okay, so the second hydrogen that comes off. And so that would be easy question that they could put on the AP test for you to recognize, what's the pKa or the pKb of that particular diprotic acid. And it would be very easy to see. So when you are looking at a titration curve like this, let me move the camera a little bit. What I want you to focus on is not as much of the math, but more so the actual species that are in each one of these parts. So what I'm going to do is over on the side here, once I get this lined up a little better, is to kind of detail out what's at each part of this. So this is going to be a weak acid with a strong base. Titration. How I know that is by this portion here. This is called the buffer region. And this is always pretty prominent on the curve. It's not straight across. You could also see here, this is going to be your equivalence point, and you could kind of see that it's above, say this is a pH of 7 here. You would see that equivalence point is not exactly at 7. So that's how you could kind of tell that this is a weak acid with a strong base. So I want you to identify what's each is the predominant species in the flask at each one of these points. So point A is going to be your weak acid. That's all you have in that solution at that point. At point B, that's where, again, you're at the midpoint there. So you need to understand pH is equal to pKa at that point. So that's going to be very important. So at that point, your HA, your acid, is going to equal your corresponding anion. So that is always going to be the case. That's why the concentration of this is the same as the concentration of this. So that's how you get a 1. So that is how the pH is equal to the pKa using Henderson-Hasselbalch equation. And then C, okay, this is where it gets a little bit more interesting. Your HA concentration is going down at this point, and your A minus is going to be a larger quantity. So your bigger quantity at point C here is going to be A minus. So that's going to be the anion of whatever your weak acid happens to be. So the HA is going down. You still have HA in there, but you don't have as much. At D, all you could say is that you have A minus being produced. Again, because all of the HA has been essentially neutralized. So this is your equivalence point. That is going to be, again, where you only have pretty much A minus. So A minus, as we saw in the other example, is going to react with the water, and you're going to make HA and OH minus. Okay, so this is going to be then a basic solution. So that is why your equivalence point is somewhere above 7. Okay, so that's indicating that. And finally, E, which is your point of past equivalence point, all we looked at was the hydroxide. So again, this is coming from the strong acid. Yeah, you still have A minus in there, but that's a small contributor to what you have in there. You could also say that you have a little bit of OH here, but I'm not going to write that in. You might see that in my other notes. Predominant thing that's driving the basic solution is going to be this anion. So again, that's going to be your focus for these titration curves, is going to be what's at each one of these points.